don't forget that. If you navigate to our course content, so quick links, and then we are lecture 2, myself, Ryan McCombs. Under the unit 2 stuff, which is about exam 2, you'll notice that I went ahead and I put a review document for Monday's class. So I recommend that you download this, print it off if you would like. Similar to the last review document for exam 1, there are way too many problems for us to go over. I have 9 pages worth of problems. There's no way that we'll be able to cover them all. And so again, I have kind of this voting system. If you let me know which ones you're most interested in covering, that will be Monday's class. If you look at the schedule, we were fortunate enough to have 2 days of review before this upcoming exam 2. So there's Monday, the 28th. This is my guided review day, right? Where we'll kind of cover this document that I've provided for you and whatnot. The Wednesday before the exam is going to be more of a free-for-all style review day. So I hope by Wednesday you'll have plenty of questions or things that you've been working on yourselves. And so basically I'll just call on people and you can ask whatever questions you would like, and I will do my best to answer them. And so that's kind of how I plan on spending our 2 review days. Of course, right, if there are questions that we don't get on the review sheet that I'm providing on Monday, and you would like me to talk about them on Wednesday, you can just ask that, right? So you can always choose to do that, or you can ask web work problems, you can ask book problems, you can ask, practice exam questions from D2L, you can ask quiz questions from D2L, whatever you'd like to cover, I'm happy to answer. Okay, I think that's all of my administrative stuff. Are there any other kind of administrative style questions or whatnot before we jump into today's topic of math? All right, well then, let's go ahead. And today we are talking about the fundamental theorem of line integrals. Darn it. All right, the fundamental theorem of line integrals is one of 2 sections that we get, I'll say, that are kind of like tricks to evaluating out line integrals faster over vector fields. So we learned in 16.2 how to evaluate a line integral with a vector field. And it's a little bit of a long process, right? And so what we get here with the fundamental theorem of line integrals is that sometimes there's a faster way to evaluate out these line integrals. And one of these faster ways is with the fundamental theorem of line integrals. And so in order to correctly state the fundamental theorem for line integrals, right, we need a little bit of a notion of what it means to be path independent. And so I kind of started with this example here, where we noticed with A, B, and C, no matter how we parameterize the curve going from 0, 0 to 1, 1, that the line integral always ended up having the answer of 2. And we theorized that even with a very complicated line going back and forth sort of deal, right, that hopefully D, the answer would also be 2, which is true, it will be. And so the trick here is going to, the fundamental theorem of line integrals will be used for when line integrals are path independent. And so we got this definition of path independent. Another way to say that, right, is that the fields are conservative. And actually, well, that means that that's the same conservative that we got from 16.1, right? Which means that we have some potential function, right? Where the vector field is equal to the gradient of that potential function. We also get some additional definitions and whatnot, which are going to be used in the statement of the fundamental theorem of line integrals. Some technical math things. We already talked about closed sets. We needed closed sets for the extreme value theorem whenever you wanted to find an absolute min or max. Remember, a closed set contains all of its boundary points. An open set contains none of its boundary points. So there are certainly a lot of sets that are neither open nor closed. They contain some, but not all, right? So it's not that they contain none, but you can make all sorts of sets that are neither open nor closed. As a fun mathematical fact on the side, there are exactly two sets that are open and closed. So you can see that these are not mutually exclusive things. The two sets that are open and closed, first one is the all real numbers. So if you're in a plane, so it'd be R2. And it's just the fact that there are no boundary points. And so it contains both all of its boundary points and none of its boundary points because there aren't any. It's like me saying I own all of the Ferraris in this room. That's technically a true statement, but it's kind of deceitful and useless, right? And so it's the same thing here. Like if, you know, it's all and none are the same when there's just not any of it. Connected, right? So connected, well, we already went over these in the video, but the fact that you can join paths in between sets sort of deal, or between any 2 points, that's going to be connected. A simple curve isn't going to intersect itself, and a simply connected region basically doesn't have any holes in it. You can't draw a circle and have part, you know, inside of the circle not being in your set. So again, we'll need these in order to bring up formally what the fundamental theorem of line integrals says. So this is actually building towards something. Now back to our original problem here that we started this off with. We had this vector field 2x, 2y, and we asked, right, can we find a potential function for this? And the answer was, well, yeah, right? We can kind of guess here something that if we take the x derivative, we get 2x. And if we take the y derivative, we get 2y. And so our vector field is indeed some conservative vector field. It has a potential function. And the main trick for the fundamental theorem of line integrals will rely exactly on this potential function. And so with that, I'd like to go ahead and transition into the new stuff for today and kind of continue the saga here. So remember that line integral originally went from 0, 0 to 1, 1. And if you think of this kind of back in terms of maybe your classic integration, well, if you go ahead and plugged in 1, 1 into our function, remember our function here was x squared plus y squared. That was our potential function. Well, then you're going to have 1 squared plus 1 squared minus 0 squared plus 0 squared. And this is going to be, well, exactly 2, which was that same answer that we got over and over and over again, right, for A, B, C, and we theorized for D. We kept on getting that answer 2. And so what we're saying is that if you're interested in calculating out a line integral with some conservative vector field, that is, right, that capital F is the gradient of some potential function here. And let's say that you have, right, that your curve has some starting and ending point, right? We'll say from point A to point B. So whatever that curve is, it has some starting and ending point, right? In our case, it was 0, 0 to 1, 1 was the starting and the ending point. Then what this seems to be suggesting is that it's okay to just plug in f of B and subtract away f of A. And this, of course, should look very familiar to the fundamental theorem of calculus that we brought up in Calculus 1, right? Which says that if you integrate from A to B of some derivative function, that this is just equal to f of B minus f of A. And after all, the gradient has a lot of derivatives in it, right? It has the f sub x and the f sub y and the f sub z if it has z's, right? And so kind of it makes sense that maybe there would be some similarity here. And so again, this was the fundamental theorem of calculus back from Calc 1. This is the fundamental theorem of line integrals here in Calculus 3. Okay. So that's a little bit of inspiration. Formally, in order for this to all work out, there are additional technical conditions here. So we do need a smooth curve joining points A and B in a planar space. We should be able to parameterize, right? F, right, should have continuous differentiable functions and a continuous gradient vector in the domain containing C. Then in those cases, we're going to have that this integral of our f dr, our line integral here over some curve C, will indeed equal f of b minus f of a. Or equivalently, like we've already written, right, capital F is this gradient vector. So you can write this as f of b minus f of a. So that right there is formally the statement, including the hypotheses and the conclusion of the fundamental theorem of line integrals. Notice that if you do have, right, and by the way, there's kind of a lot of definitions floating around here depending on what you're looking at. So you can talk about that, you know, some integral is path independent. You can say that a vector field is conservative, or you can say that there exists a potential function. Right? There's kind of lots of ways depending on if you're looking at and saying a statement about an integral, a vector field, or a function, right? Conservative vector field, path independent integral, or again, a potential function. So if you have this thing that's right, will work with the fundamental theorem of line integrals, then if you have any closed path, so again, a closed path is one that starts and ends at the same point. So that is A is the same thing as B. You start and end at the same point, right? For most curves out there, right, you maybe start and end at different points. But for a closed curve, you start and end at the same point. Well, if you start and end at the same point, and this thing satisfies the fundamental theorem of line integrals, right? It's path independent, so it has a potential function sort of deal. Well, then f of b minus f of a, if a and b are at the same point, it doesn't matter what the function's value is, right? Maybe f of b is 7. Well, then f of a is 7. And you're going to have 7 minus 7. And so you're always going to get 0. So again, if you start and end at the same point, right, you're always going to get out 0 here. All right, so here's where we sit. Number one, we like conservative vector fields because they are path independent. And so we can hopefully use this fundamental theorem of line integrals on it. And of course, we'll like them even more because we can find their potential function. Then the line integrals are extremely easy to calculate. And so what we need to work on a little bit more is actually finding potential functions. So the natural question is, given a vector field, is there a way to tell that it actually is conservative or that a potential function exists? I'll just say has potential function. And then second of all, okay, if we know that we do indeed have a conservative vector field, how do we go about finding the potential function? So these are the last two questions that we need to tackle in order to have a good understanding for this topic. So in order to answer the first one, how do you know if it's conservative? I'd like to give you this theorem called the component test. So the component test will work if you're in the plane, that is that you should have a vector field with P's and Q's. Later on, we will upgrade this for space, and that's going to be in 16.5. So that's not going to be on the upcoming exam and stuff like this. But the component test will be, of course, fair game. So if you have a vector field that has two components, P and Q, in a plane, and you have some open, simply connected region D. Suppose that P and Q have continuous first order derivatives, and that if you take the partial derivative of Q with respect to X and P with respect to Y, and these things happen to be equal to one another, then F is conservative. As a quick side note, right? If you think about if F is conservative, aka is the gradient field for some potential function, then that means that P and Q would have to be F sub X and F sub Y, right? If this is the gradient of some potential function, then this is F sub X and F sub Y. So this right here, if you take Q and take the X derivative of it, so take Q and take the X derivative of it, that would be F sub Yx, right? Because Q is already the Y derivative, because it's again the gradient vector. And P, right, if you take the partial derivative with respect to Y, this is going to be F sub XY. And so basically this right here just says if it satisfies Clairaut's theorem, if mixed partials are equal to one another, then there will exist a potential function. And you can go about finding it. So this is just a kind of a clever reworking of Clairaut's theorem, nothing more. And so let's go ahead and get some practice with this. So I have a conservative vector field. I would like to show that it's conservative. We're going to work on finding a potential function, and then we'll use it to evaluate something. So here's kind of our first full strength problem for the fundamental theorem of line integrals. So, okay, well, in order to show that it's conservative, we can use our component test that we just came up with, right? So I'm going to go ahead and identify. Again, my first component is P, and my second component is Q. And notice there's a little bit of mixing sort of deal. So for P, I'm going to take a Y derivative, and for Q, I'm going to take an X derivative. So I'm going to do P sub Y, or if you like the partial notation, by all means, you can stick with the partial notation. So if I take the derivative of this with respect to Y, I'm going to have negative e to the X sine Y plus 1. So again, I take my P, and I take the derivative of it with respect to Y. Next up, Q. Q, we're going to take the derivative with respect to X. If I do that, I get 1 minus, and the derivative of e to the X is itself. Sine of Y is along for the ride, and the derivative of 3 is 0. And so indeed, we can see that P sub Y is equal to Q sub X. These mixed partials here are indeed equal. And so by the component test, we know that this vector field right here is conservative, aka it has a potential function. So this is part A. Part B, we'd like to go out and try to find this potential function. So again, if this really is, right, a conservative vector field, then that means that it's equal to the gradient of some function, aka that the first component is an X derivative of some function, and the second component is the Y derivative of some function. And so you can imagine, if you're interested in finding what F is, let's go ahead and maybe take this bit right here, maybe just our first component, that's supposed to be an X derivative, and let's undo that X derivative, aka take an antiderivative or do an integral. So I'm going to go ahead and take my first thing, this e to the X cosine Y plus Y, and I'm going to do an X integral. So I'm going to integrate this with respect to X. Okay, do an antiderivative, undoing the fact that this is F sub X. Okay, so if we do an antiderivative with respect to X, let's see, we're going to have the integral of e to the X is itself. Cosine of Y is a constant. It's along for the ride. When I integrate Y, well, Y is constant. So when we integrate a constant like 2 with respect to x, right, it becomes 2x. So likewise, yx here, plus some constant of integration. Now, constants of integration, when you have multivariables, are a little bit nasty. Constant of integrations don't actually have to be true constants. That is, if this constant of integration right here, let's just think about for a second, was equal to 7 plus y plus cosine of y, or something like this, then if you were to take the derivative with respect to x, after all, we're kind of isolated on x, and we're taking the derivative with respect to x to get that first component. If you had any number of y's in here, so long as there are no x's, the y's are constant with respect to x. And so just like 7, when you take the derivative of 7 with respect to x, you get 0. Likewise, if you take the derivative of y with respect to x, you get 0, because it's constant with respect to x. And likewise, even like weird combinations of y's, right? You could even do like cosine of y raised to the yth power and stuff like this. So long as there are no x's, x can't detect it, right? Because it's constant with respect to x. So in fact here, your constant function could have any number of y's in it as well. So just like we use f of x to say, right, it could be a function of x, it's allowed to have as many x's in it as it like. Likewise, we'll use a constant function, but it can have as many y's in it as it would like. Because if you take the derivative of something with just y's with respect to x, we can't really detect it. So I know some of you out there, I'm sure, were thinking about, well, how do you use this second component, right? Why did you start with the first and kind of forget about the second bit? Well, this is what's going to be used in order to help us figure out what this needs to be. So remember, the second component there is supposed to be if we take the derivative with respect to y. So right now, I have an idea kind of what my f function looks like. Looks something like this, but I don't know what this constant of integration looks like. And in this case, it can't have y's. So I'm going to go ahead and take this. Let me move this over a little bit. And I'm going to take the derivative of it with respect to y. So if I take the derivative of this with respect to y, let's see what happens. We have negative e to the x sine y plus x plus c prime of y. Because again, we only have y's in this, so you're allowed to use the prime notation if you'd like. If you'd rather use the subscript notation, you're certainly allowed to. But we need to take the derivative of this, and we get c prime of y. Now we're going to compare that with what we know the answer ought to be. The answer ought to be, right, according to our Q, x minus e to the x sine y plus 3. And again, what we got was negative e to the x sine y plus x plus some derivative of some mysterious function with respect to y. And so from here, we can see that we have quite a bit of cancellation. We've successfully accounted for this e to the x sine y business. We've successfully already accounted for x. And what we're left with is that this derivative function with respect to y must be equal to 3. And so if you're interested in what c of y, without the derivative there, must be, well, if its derivative is equal to 3, if we do an antiderivative, we're going to get 3y. Again, this is a function of y's, and we took the derivative with respect to y. So if you do an antiderivative to figure out what this function needs to be, because after all, we're trying to figure out what should we plug in right here. What should our f function be equal to? And the only mysterious bit left is this c of y. So when you integrate here, c of y is equal to 3y plus a true constant. So I wouldn't reuse c necessarily. K is another common one that a lot of textbooks use. But if you want to use d or whatever, that's perfectly fine as well. So now our final answer here is going to be well, we're just going to plug that in. So the answer for B here is e to the x cosine of y plus yx plus 3y plus any constant, right? And so since it just says find a potential function and not find the most general potential function, I'm going to have our constant be 0. That's the one, that's my favorite. All right, so there is the answer for B. And finally, we have some tricky curve here, r of t, and we'd like to actually evaluate out a line integral. And so if we'd like to evaluate out the line integral, and we have something that satisfies the fundamental theorem of line integrals, then of course, my dream here is going to be to use this f of b minus f of a business. That's what the fundamental theorem of line integrals gets us. If you want to evaluate out a line integral, according to the fundamental theorem of line integrals, we can use this. So the only question is, what is b and a? Well, b and a are supposed to be the starting and the ending points. We have starting and ending times for this thing. So I need to take a minute and figure out what the points would be. So the starting point will somehow be associated with our starting time of 0. And so if I plug in 0 into my parameterization, right, we're going to have the point 0 and sine of 0 is 0. If you're interested in the ending point, well, this is of course associated with the ending time of t equals 1. And so if we plug that in to our parameterization, we're going to get 1 and sine of 1. And so, according to the fundamental theorem of line integrals here, well, we need to plug in some stuff, right? So this is going to be my f of b business. So this is going to be e to the 1 cosine of sine of 1 plus sine of 1 times 1 plus 3 sine of 1s. So that's my f of b. And my f of a, which was 0, 0, much nicer thing. Well, let's see, the x and y will be 0, the 3y will be 0. The only stuff that's not 0, right? E to the 0 is 1, and cosine of 0 is 1. So this is actually 1 times 1. This is not an especially beautiful answer here. I give you that. But my claim is, if you were to try to actually solve out this integral, not using the fundamental theorem of line integrals and just using kind of the classic 16.2 method, right, where you calculate out r prime of t and all that sort of stuff and plug it in, that integral there will be darn near impossible. And so if you have a free half an hour or hour or something like this, verify my claim and just see that even though this doesn't say that you have to use the fundamental theorem of line integrals, basically it's the only option that's doable in any reasonable amount of time without heavy, computers doing the lifting for you. All right, any questions on this here? So now that we've, I guess, gone over the technique, let's try to distill this as best as we can into, in general, how do you go about finding potential functions? And so if we go back and we kind of classify our steps again, we took the first component and we integrated it with respect to x. Because again, after all, this was supposed to be f sub x. And so by doing that, by doing this antiderivative, we get a potential function plus some constant that could have y's in it. We couldn't really detect what kind of y function there would have to be with just this information. The rest of the time we spent trying to solve for this function, right? The c of y. In order to do that, well, we took the derivative, right? So we took the derivative of our answer, f plus c of y, with respect to y, and we set that equal to q, because after all, q was supposed to be f sub y. From there, we were able to solve for c prime of y. Right, so in our last problem, we were able to find that c prime of y was equal to 3 by canceling stuff out. Wasn't all that bad. And then we integrated both sides, right? So we integrated with respect to y. Sorry, apparently before I was using g at some point. But yeah, if we integrate both sides with respect to y, we'll get this function that we're interested in. So this right here, these are the key steps in order to find a potential function. And we'll see, we'll play this same game again as I alluded to in 16.5 with three-dimensional functions with x's, y's, and z's. And in fact, I've included on the last page here, although we certainly will not have time to go over it in great detail. But if you have x, y's, and z's, then as you can imagine, if you take an x integral, or really what we're doing, we're looking at the x derivative, right? That it's going to have a hard time detecting not just y's, but it'll also have a hard time detecting z's. So you'll have to play this game basically 3 times rather than just 2 times if you have more variables, because x derivatives are really good at detecting x's, but they're not really good at detecting y's or z's because, well, they're constant with respect to x and they'll just all go to 0. Okay, let me pause again here and just see if there are any questions before we move on. Oh, sorry, yes. Yeah, so the question was, we started with P, integrated that, and then used the Q to basically refine our guess, right? But the bulk of the heavy lifting was done by P. And so the question was, could we do that in the opposite order, right? Could we take Q first, integrate that with respect to y? After all, Q is supposed to be the y derivative of some potential function. So could we integrate that to get our guess? And then kind of work in the other direction, right? Take a derivative with respect to x and set that equal to p. And yeah, that would certainly work. Yeah. So yes, I've given you, this would really say maybe a technique for finding potential functions, right? But there are multiple legitimate techniques for finding potential functions. So if you'd like to start with a different one, that's certainly fine. All right, moving on, I have kind of an interesting, tricky problem sort of deal. I have a vector field, and I would like to show you that it satisfies the component test. So let's go ahead and take some derivatives, p with respect to y and q with respect to x, and show that hopefully these things are equal. So again, p is our first one here. We're going to take the derivative with respect to y. You can see that we're going to need to use the quotient rule. So we're going to do the derivative of the top times the bottom minus the top. So minus and negative will be plus, times the derivative of the bottom. And the derivative of the bottom with respect to y will be 2y, all divided by the bottom squared. Let's take one line here to simplify. We have 2y squared here, and we're subtracting away y squared. So when you have 2y squared and you subtract away 1y squared, of course, we're going to have 1 left over. Notice that you're also subtracting away an x squared. So this is going to be y squared minus x squared. So now the numerator is completely simplified here, and then in the denominator, just is what it is. Okay, let's play the same game here, but now taking an x derivative. with Q. So Q is our second component here. So when I take the derivative of this, well, okay, again, quotient rule. We have the derivative of the top times the bottom minus the top times the derivative of the bottom with respect to x, all divided by the bottom squared. And again, if you carefully simplify, I hope that you will notice that the numerator simplifies to the exact same thing. That is, we have a positive y squared, and we have minus x squared once we've simplified down. Because there's a positive x squared here, and there's minus 2x squared here. And so we can see that this satisfies, right, the main bit of the component test. Now, with a closed curve, nice beautiful circle here, starting and ending at the point 1, 0. All right, cosine, comma sine, that's radius 1, kind of the classic polar parametrization. We're going from 0 to 2 pi. So we have a nice closed curve. Now, according to theorem 3.8, back here, if you have a nice closed curve and you do a line integral with a conservative vector field, or if you take that in the integrals framing, that it's path independent, you ought to get 0. If you carefully actually do this integral out, though, you see that you get 2 pi. My claim is that there's no mistake in any of the work here. I've double and triple checked it. So, you know, by all means, you can double and triple check it yourself. But if you go ahead and plug these things in, right, the fact that you have x squared plus y squared, you get sine squared plus cosine squared, you're going to get 1 here, 1 squared. And so, yeah, when you carefully do this, you do indeed get 2 pi. And so the question is essentially what gives, right? Why isn't this 0 here? And so like I said, this is a bit of a tricky one, but it goes into the hypotheses here, mainly that for the component test to truly say whether or not you have a conservative vector field, we skimmed over kind of quickly here that you need an open, simply connected region D for the domain of your vector field. And for this vector field right here, notice that its domain, the things that you're allowed to plug in, and you would get out a real answer. There's a lot of things, but right, I am a little bit worried about this division. If you were to ever divide by 0, right, that would be an issue. Sadly, you do divide by 0 at exactly 1 point. What is it? What is the 1 point that you divide by 0? 0, 0, right? So if x and y are both 0 at the origin, you divide by 0. And so if I go back to my picture here, the domain doesn't include the origin, which again, this unit circle goes around. So the domain is not simply connected. Remember, according to our definitions here from the, I guess we really did this in the video more than anything. Simply connected means that you're not allowed to have any holes. And so the fact that you have this hole in the middle kind of ruins the component test. And so this right here is not actually a conservative vector field, even though it satisfies kind of the highlight of the component test. The fact that it's not simply connected is an important restriction here. Otherwise, you get this kind of nonsense, where instead of 0, you get some other answer. So more than anything, I mean, this is kind of just mathematically interesting. But again, kind of whenever you have a mathematical theorem, you do have to be careful about what the hypotheses are. And if you try to use the conclusion for something where you don't have the hypotheses satisfied, you're going to get sometimes surprising and nonsensical result. So in this case, it is not conservative. And so since the vector field is not conservative, because again, it didn't satisfy the hypotheses, it's not alarming that you get 2 pi here instead of 0. Theorem 3.8 is only good if you have conservative vector fields. So does this contradict? No, it does not, since F is not conservative. Okay, so a little bit of a tricky question there. Let's get back to, right, kind of a more standard bread and butter style question, what you're likely to see on homework, quizzes, exams, stuff like that. I have kind of a quick conceptual one that would make maybe a fine true, false, or multiple choice style question. And then I have kind of a classic, again, standard response style question here. So, okay, we have some curve, and I've drawn a contour map. That is a bunch of level curves, right? So I have a bunch of level curves here. My F is continuous, and I'm interested in finding this line integral here. The line integral where the vector field is, right, this gradient. So if you go back and, maybe out of paranoia, since I've just been talking about the hypotheses for things and making sure it's satisfied, right? You go back to the fundamental theorem of line integrals, and you can verify that this setup does satisfy the conditions for the fundamental theorem of line integrals. And so this is going to be equal to some f of b minus f of a. But we don't have an equation given to us, right? Really, we have a picture of what the contour maps look like. And if we zoom in, okay, I can kind of identify, we start down here, this would be my A, and I guess we end up here, this would be my B. Can anyone tell me what f of B is? Yeah? 50, yeah, exactly. So remember the contour map, this is telling you the outputs, the K values, for what the function would output if you're along this level curve. So if you're along this level curve, anywhere along it, the function will output 50. That's what a contour map or the graph of the level curves tells us. And likewise, if you're anywhere along this curve, the function, the output will be 10. So this is just going to be 50 minus 10. And so the final answer here would be 40. So again, not a lot of calculations or things like that to do for this sort of problem, but it does test whether or not you understand the concepts. What does a contour map actually tell you, right? The setup for the fundamental theorem of line integrals, that you can use this here. So it does test some kind of key concepts. Okay, well, last problem here. I'd like to take this vector field, hopefully show that it satisfies the component test. Then we're going to go about finding a potential function. And then lastly, we'd like to use that potential function to actually do something. That is, evaluate out a line integral, hopefully using the fundamental theorem of line integrals. So this is kind of a classic style question here. So in the interest of time, let's kind of jump forward here. So you have the IJ notation rather than the kind of bracket notation, but that's fine. This is P, this is Q. We're going to take P sub Y, that's 2x. We're going to take Q sub X, that's 2x. Notice that these are the same thing. So yeah, F is indeed conservative, thanks to the component test. By the way, if you were paranoid, given my last example here with the component test, and you started to think about, okay, what is the domain of this vector field, right? Are there any things that I could plug into this where it wouldn't make sense? And luckily the answer is no, right? There's no division, there's no square roots, there's no natural logs, there's nowhere to make this undefined. So our last one, really the fact that we divided by this x squared plus y squared was the thing that we got a hole. And then we didn't have a simply connected domain. And then the component test was null and void. Okay, now let's go ahead and try to find a potential function. So I'm going to integrate p with respect to x. After all, if this is a potential function, right? So this is a gradient field. This is supposed to be f sub x, and this is supposed to be f sub y. So by integrating the first thing with respect to x, I should find a good f. So this is going to be 3x plus x squared y plus some function that could have y's in it. Now let's go ahead. This is what we think f is right now. We're going to go ahead and take the derivative of this with respect to y. So f sub y is going to be equal to x squared plus c prime of y. And this is what q ought to be equal to, right? Q is supposed to be this f sub y business. And so we can see that according to q, this is equal to x squared minus 3y squared. Again, x squared minus 3y squared, I just set it equal to q. Just as before, we can go ahead and use this to solve for c prime of y. With c prime of y, we can calculate c of y just by taking the integral. So when I integrate both sides, I'm going to have negative y cubed plus a true constant. But again, we're just looking for a function. So we're going to set that true constant to 0. So my final answer here, if I was to plug this in, right, is just going to be all this stuff minus y cubed. So that right there is equal to my potential function. A potential function, right? Again, it could have a +5 there if you'd like, or whatever your favorite constant is. And then lastly, we're going to use that to evaluate out a line integral. And so we need to know, again, what our f of b is and our f of a is. And in order to get that, well, again, we have a nice curve, and we have a starting and ending time, but we don't have a starting and ending point. And so to figure that out, we need to plug in 0, and we need to plug in pi. And so if I plug in 0, I'm going to have 0, comma 1. And if I plug in pi, I'm going to have 0, comma negative e to the pi. Cosine of pi being -1, that's where the negative comes from. So plug that in and you win the game. So just plug in these points into our f from up here and you'll have it. I see that I am out of time, so I appreciate you guys sticking around. I guess just out of my own, I don't know, necessity, I will finish writing this one up. If you care to stay, you certainly can, and then I'll take questions as soon as I get done writing this. So let's see, f of b minus f of a. Let me go ahead and move this over, kind of clean this up a little bit. And so if I was to plug in this e and negative, 0 and e, negative e to the pi, let's see, I would have 0 plus 0, and then minus e, negative e to the pi cubed. It's a little bit annoying, but okay. And subtract away f of a, so 0, 1. And so again, if I plugged in 0 for x, it's quite a few zeros. And if I plug in 1 for y, it's something like this. And so my final answer here would be positive e to the 3 pi minus a negative 1. Hopefully I didn't make any silly algebra mistakes. Please let me know if I did. But yeah, this is what I believe the final answer is. All right, so with that, we are done with all of the new content.